Hey everybody, welcome back. So today we're going to learn about how to use the kinematics equations of motion in order to solve problems and make predictions about the motion of an object. So when we start out, the first and most important thing when we go through these is to make sure that we know when we're looking at these equations, we know what the symbols mean. All right, we know what delta x and v and a and t mean and understand that and what units are on each of those measurements so that we can pick that apart in a problem. Because a lot of times where students have their troubles is understanding how to set up the problem, and that's because they don't have a really firm grasp on knowing what those symbols stand for and how to put them into an equation. All right, it's not usually the math that's the problem, it's the setup of the problem. Okay, so the first thing is displacement. We learned what displacement is. It's how much an object has changed its position. Say that a different way. It's how far is the object from its starting point. That's what displacement is all about. We're going to use the symbol delta x for displacement in the equation. And the standard units for displacement are meters. But you could measure displacement in feet or miles or centimeters or kilometers. Any unit of length really is going to be a possible unit for displacement. But the standard unit is meters, and that's the one we're going to use the most. The next symbol is V, and V stands for velocity. Velocity is defined as the rate of change of an object's position. All right. So what does that mean? It means how fast is it moving and what direction it's going. All right. And we talked about this in class as well. The units that we're going to use for velocity are meters per second. All right. That's the standard unit. But you could use miles per hour, kilometers per hour, or feet per second. Those are all examples as well. All right. A stands for acceleration, and that's going to be the rate of change of an object's velocity. So think about what that means. It means how rapidly an object speeds up, slows down, or changes direction. When we say changes its velocity, that's what we mean, right? Speed up, slow down, change direction. So acceleration tells us how rapidly that happens. Keep in mind, an object can have no acceleration even if it's moving, right? If it moves with a constant velocity, moves in a straight line, constant speed, it's not accelerating at all. Its acceleration would be 0. So the units we use for acceleration are typically meters per second squared. That's the standard, but you could use feet per second squared, kilometers per hour per second, miles per hour per second. Those are all examples. And then the last symbol is T. T stands for time. We all know what time is. It's how we sequence events. And it describes to us how long a particular event takes. All right, so the standard unit that we're going to use in physics are seconds, but you could use minutes or hours or days, things like that. So the symbols, delta x, v, a, and t, those are the things we're going to be using in the equations. Now the next slide shows the actual equations. So here they are. All right, so the first equation here, you'll notice there's two different v's here, and same thing here. So they're both velocities, but they're different examples of velocity. So v sub f stands for the final velocity, so that's at the end. V sub o stands for the original velocity. So we're saying the final velocity equals the original velocity plus acceleration times time. Vf equals Vo plus At. All right, the second equation says delta x, so that's displacement. Displacement equals Vo times t, so that's original velocity times time, plus 1/2 times the acceleration times the time squared. Now, please note, in that equation, the only thing that's squared is the t. It's not the whole term, just the t. And then the last equation I like to call the no time equation. It says final velocity squared equals original velocity squared plus 2 times the acceleration times the displacement. So this one, like I said, I like to call the no time equation because it's the only one that doesn't involve the letter t. Okay. All right, so next let's talk about some steps we can use for actually solving kinematics problems. And really, you should write these down and you should follow this every single time you do a problem. You should set it up this way and do it this way every time. If you want to be successful and be able to solve these problems and not get stuck, this is the way to do it. So the first thing is visualize the situation asked in the problem. So since we're in physics and we're talking about physical things that really happen, it's really easy in many cases to visualize what's happening. All right, we're going to be talking about, cars moving along or, people or things like that. So I think it's pretty easy to be able to kind of picture in your mind what's happening. Then it says write down what known information you have from the problem and what you're trying to find. Pay attention to units, they're a big clue. So you want to make a list. Every time you do one of these problems, write down a list and write down what things we have, we're given, and what things we need to know. And the best way to be able to solve that or write that down accurately is to look at the units. If I see, for example, a 10, but I don't know what a 10 what, right? I have to pay attention to the units and say, oh, it's 10 meters per second squared. Well, meters per second squared, that's an acceleration. So I'm going to write down A equals 10 meters per second squared. But if I saw 10 and then it said seconds, I know that's not an acceleration. Seconds are not a unit of acceleration. They're a unit of time. So T would be 10 seconds. Okay, so watch those units. They're super important. Speaking of units, if any units need to be converted to the standard units, do this before going any further. So for example, if they tell us, oh, the car started out at 55 miles per hour. All right, well, 55 miles per hour is a velocity, but it's not in the standard unit. We're going to convert that to meters per second before we go any further. Then find an equation that connects the known quantities and the unknown thing that you're looking for. And make sure the equation only has one unknown. So we're going to look at our three equations and we're going to say, all right, I need to know, let's say, the time. All right, which equations have time in them? And what do I know in my list that can give me the time and only have one unknown in the equation? We can't have more than one unknown. Once you choose which equation, you're going to isolate the variable you're looking for using algebra. So what you'll do is you'll say, all right, if I need to know t, I need to get t by itself on one side of the equation. Or if I need to know a, I need to get a on one side of the equation all by itself. Then we substitute the numbers from the problem into the expression and use our calculator, calculate the result. And we make sure to put units on the answer. So the last step is to plug in the numbers, crunch the numbers, and see what we get for the answer. And make sure we put units on it. All right, so let's look at an example problem here. And this example says a physics student skis down a hill, accelerating at a constant 2.0 meters per second squared. If it takes her 15 seconds to reach the bottom, what is the length of the slope? All right, so picture this. A person starts at the top of a hill, they ski down to the bottom, it takes 15 seconds, and they're accelerating as they go. So they're getting faster as they go down the hill. I think that's pretty easy to picture that. All right, one thing it doesn't say in the text of this question, but I'm going to kind of throw in there is that we're going to assume for this problem that the skier starts from rest. They start at 0 meters per second, okay? So they don't have like a head start. All right, so we visualize the problem. Now we write down everything that we know and what it is that we're looking for. So I know that they have an acceleration of 2 meters per second squared. And I know that because it says it. Accelerating at a constant 2.0 meters per second squared. The units tell me, and plus it says accelerating at. All right, then I know that it took 15 seconds to do it because it says that, 15 seconds to reach the bottom. And I said to you, we're going to make the assumption that they started from rest. So their starting velocity, their original velocity is 0. What does it want to know? What is the length of the slope? All right, what is the length of the slope? Well, that's just a different way of saying how far did they ski from the top to the bottom? Or another way of saying, how much has their position changed from the top to the bottom of the hill? That's a displacement. So I'm going to write delta x equals question mark. So I want to see every time you do a problem, I want to see you set it up like this. Write down what's known, write down what you need to know. That should always happen. It's going to help us guide us into the right solution. All right, so I have A, T, V, O, and I need delta x. So the next step is to figure out, well, what equation should I use? So if I go back, I take a look at my equations. If I'm trying to find delta x, well, I certainly can't use the first equation because it's not even in there. So this is out. And I can't use this either because there's two unknowns. I don't know VF and I don't know delta x either. So this is not going to work. When I look at this one, this will work because I'm looking for delta x, I know VO, I know T, and I know A. So I can plug in everything to this equation. So that's what we're going to do. So I'm going to write the equation down. I'm going to write delta x equals VOT plus 1/2 AT squared. Okay, now the next step in the directions said to isolate the variable you're looking for. In other words, get it by itself on one side of the equation. Well, here, I already have that. Delta x is already by itself on the left-hand side. I don't need to do any fancy algebra to get it by itself. So we can proceed right to the next step, plugging in the numbers. So if I do that, well, VO is 0, so it's 0 times 15. Well, 0 times 15 is 0, plus 1/2 the acceleration, which is 2 meters per second squared, times the time squared, 15 seconds, but we're going to square that. So we can use our calculator to do all of this. So I have a half times 2 times 15 squared. Well, we could do this. Half of 2 is 1. And 15 times 15, that's 15 squared, is 225. So 225 times 1 gives me 225 meters. And I know it's meters, first of all, because it's a displacement. And second of all, because if we look at the units, this is meters over second squared, and this is second squared. So we are left with meters. So my answer is 225 meters. And if I remember that a meter is about the length of my leg, then 200 meters is about a little more than 2 football fields length. All right, so that seems like a reasonable answer for the length of a slope. And we can go from there. So you're going to see more examples of this both in class and also additional videos that I have available to you. So you can check those out. But the main thing is you got to do lots of practice. All right, you're not going to get it just by watching the video and saying, oh yeah, well, I understand that. You don't really understand it fully until you actually do it. Lots of students will try, they watch, and they can follow along with the problems when they're done in front of them. But then when they have to do the problems themselves, they get stuck because they don't have a full understanding yet. The only way you're going to have a full understanding is put the reps in. Practice, practice, practice. So we're going to do lots of practice over the next couple of days, and hopefully you'll be in good shape with those types of problems.